just before the break, we were looking at these exponentially tilted distributions, and I'd introduced them as a way of kind of looking at a new family of distributions for which you can look inside, that rather than just taking, for example, a normal distribution and changing the mean, or taking any common distribution and just changing one of the parameters. This is sort of another way to get a family of distributions to look inside. But that's kind of lying to you a little bit. And that's because if you take this example a bit further, the gamma distribution, and if you write out the actually exponentially tilted PDF, this is what it looks like here. And this mess, because there's e to the something here, e to the something here, you can do a bit of algebra and bring them together and get e to the something else in terms of this m tilde, where m tilde is just this thing, m on 1 minus m theta. And you can conclude from that, when you exponentially tilt a gamma distribution, you just get another gamma distribution. So sometimes tilting is just really boring, and actually it's quite common. So this is, since it happens there are so many examples, I found the page in my PhD supervisor's textbook that he wrote on this topic and just took a screenshot of it because I was too lazy to copy it out. But for example, the exponential distribution, if you exponentially tilt it, you get another exponential. Same with the gamma, as we just saw. The binomial distribution, Poisson distribution, normal distribution, multivariate normal distribution. So pretty much anything that's called this like natural exponential family of distributions, when you exponentially tilt, you stay within the family. It's almost by definition. But okay, so one important note about when you're doing this tilting. So as I showed on the plot before, when you have a theta that's positive, you push the distribution to the right. So that means your probability of getting a very large event increases. And so for the examples we've been looking at, that's really what you want to do. You want to be having theta positive to make our rare event less rare. And then theta negative does the opposite effect. It decreases the likelihood of seeing those really large values. But just like with the gamma case, when you went, there was some limit that you could go to. You could push theta to be up to, in that case, 1 divided by m. And so if you were to take just any distribution, you can ask the question, what is the largest value you can tilt this by? And that's determined by this moment generating function. If you make theta get bigger and bigger, it eventually just becomes infinite. So how large can I go before it becomes infinite is useful to know. And this turns out to actually be a way to define a category of just probability distributions. Some distributions, if you push theta even like infinitely small amount above 0, it all blows up straight away. You just can't tilt it. And those distributions are called heavy-tailed. And they're the ones that you use, like I've written some examples here: Pareto, log normal, Cauchy, Weibull with certain parameters. And so these are the ones that sort of naturally have a high probability of really large outcomes. So these crop up all the time in the insurance literature on catastrophes or in insurance in general, because it's usually the case that for example claim sizes that come into some insurance company, most claims are very small, but then there's a sizable proportion of a gigantic claim coming in. So you would use this kind of heavy tail distribution for that. But for the specific, for the case of exponential tilting, because it doesn't have a moment generating function that is defined for positive theta, you can't actually use this exponential tilting on those distributions. It only works in the case of light-tailed distributions. Yeah.
Is there really a specific definition for heavy tail function in distribution?
This is it. This is the definition. If it has a, if you can't push the moment generating function above 0 and get some number, then it's heavy-tailed. And so, yeah, so if in...
It kind of has to converge faster than an exponential function?
Exactly, yeah. It's, you can't normalize this thing, basically. When it's already as heavy as it can get, and when you add in the e to the theta x, it's just too heavy that you can't do the integral underneath it to normalize it. Okay, and so the second thing I mentioned before with the cross entropy is you're assuming that you can actually simulate from these distributions. And so I wanted to show you a simulation algorithm that works. But if you have a density that you want to simulate from and you can't do it any normal way, you can always fall back to this one called acceptance-rejection. And I want to show you not because it's particularly interesting for rare events, but because it gets you in the mood for what I'm coming next, which is Markov chain Monte Carlo. So in acceptance-rejection, I'll show you the picture first, and we can work backwards to the algorithm, perhaps. So say that we want to simulate from a distribution which has this PDF here in blue, the sine curve plus 2. So this thing is not a standard distribution. It's not normally distributed, not exponential. But for whatever reason, you want to simulate from it. So the trick is with acceptance rejection, you find some other distribution which has a PDF which is greater than it when you scale it by some factor. So this blue line here, it shows you the density of a uniform distribution. If you take a uniform distribution between 0 and 4 pi in this case, and you multiply it by 16 pi, that's c equals 16 pi here. So that's what you have to start with this for acceptance rejection to work. So you've got your density you want to simulate from, you dominate it by a constant times some other density, assuming you can sample from this other density. Okay, so then to get one sample from your crazy density, you keep trying, you keep sampling from your simpler one, f of y, and so you get one proposal y, and then you also just take a uniform random variable, and it's kind of like flipping a coin. With some probability, you say, okay, I'm happy with this y, I'll accept it. But if the coin comes up tails, then you try again, and you simulate another y. And the weight of the coin is this ratio, the original density at the point y divided through by c times y's density. And so what this is actually doing is if you all the points on this plot here are different proposals, different y's. So they're effectively, you've sampled uniform random variables between 0 and 4 pi, and then for each of them I generate a uniform random variable between 0 and 4. So that's why the plots have the uniform variable is the sort of the y component of these points. And if that y component happens to be smaller than the target density, we accept it. So all these ones which are circles have been accepted. And then I've drawn like a line down to where they are on the x-axis. And so you can kind of see there's more being accepted around the areas that have like the top of the curve in the sine curve than down here in the hump of the sine curve. And maybe that has that's sort of what you would expect from the situation. Okay, so putting that to one side, we'll get back to that near the end of this. But we can spend a bit of time on Markov chains. So I guess the theoretical definition is really, well, it's easy to put that on paper, it's a bit boring, but I'll then turn to some code to simulate some of these, and you can get an idea, get a feel for them. So there's lots of ways to define these things, but we'll look at a discrete time process, stochastic process, which takes values that are continuous. So we start off, maybe x naught equals 0, and then x1 equals 3.75, and x2 equals 5.68, etc., etc. That might be one Markov chain simulation. So the definition, what is a Markov chain, is any process that has the Markov property, and that is saying, I want to know the probability that the chain at time, something happens about the chain at time n, and I've got the whole history of the chain, all the values before it, from time equals 0 up to time equals n minus 1. If all the probabilities related to time n, if they're independent of everything before n minus 1, they're independent of the history of the process, then it's a Markov chain. It has the Markov property. So there's lots of distributions that you can generate from this kind of stochastic process, and this is not at all related to where we're going, but I put in a link. I gave a research talk recently on this kind of thing called the phase type distribution. It's when if you run a Markov chain until it hits some specific state, and you look at how long did it take to get that state, and you look at that as a way to generate random variables. That's what this phase type is. And probably you're not so interested in seeing just the research talk, but it was because I arrived here and everyone was asking me lots of questions about Australia. It was like the first half hour is just photos of kangaroos and stuff. So if you're really bored and you just want to look at something, then I recommend that. Anyway, I won't go through that again now. But there's the link. Okay, so what is important for us is that a lot of Markov chains have this property that they have a stationary distribution. And so what does that mean? It means that if, say, pi is a stationary distribution, and if is a stationary distribution for a specific Markov chain. I should put it that way. If I simulate a value from that distribution, and then I move the Markov chain forward one moment in time, given that value of x0, then that is also distributed according to pi. And if I move that forward another moment, and so on for forever, x2 given x1, that's also distributed according to the same distribution pi. In a sense, you're not going anywhere. If you start a Markov chain in its stationary distribution, you're sort of sticking around the same thing. Nothing special is happening. So that's actually the whole point of Markov chain Monte Carlo. Is what you do is, if you have some tricky distribution that you want to simulate from, some really complicated thing, you make a Markov chain that has your tricky thing as the stationary distribution. And because normally generating Markov chains is quite simple. So what you can do is you can simulate identically distributed variables from your pi. Note, it's not IID. Even though, say, x1 and x2 here, these two things have the same distribution. They're not independent from each other. So this is the fundamental difference from the previous, like the crude Monte Carlo. Every time you make a replicate from your distribution, they're all independent from each other. In this case, you're losing that nice property, but sometimes you have no option. You have to do some dirty thing like this. Okay, so this is the goal, but it's kind of like a chicken and egg scenario here. If you could simulate from this pi, then you can simulate from the pi. So you need pi to simulate from pi, kind of thing. So this is something that needs to be addressed.
Excuse me.
Yes?
I don't understand the utility of using this type of Markov chains when it's stationary, because if it's stationary, if you want to have x n, and if you know x n minus 1, you can just use pi. Is what you explained. Instead of the stationary distribution, I don't understand the interest of Markov chains.
Well, the Markov chain part is how you move from one state to another. You need to define. It's called a transition rule to say I'm in state here. Where do I go next? And so typically it's quite simple to simulate, like moving from one location to the next. And if you just look at where you land, if you take it, you move one step and you move another step and you do this 100 times, if they're all from the same distribution, then you can use that as a sample from pi for your, instead of crude Monte Carlo where you sample from pi directly, you could just move the Markov chain around 100 times and take wherever it lands to be the 100 things you use in Monte Carlo.
Yeah, but you have to know pi. If they're stationary, you only have to know pi, and then you can replicate whatever n you want to simulate.
Well, okay, so this is in this case you actually don't need to know pi to simulate according to this method. Yeah, my pen's not working anymore. So all you need to know is pi up to a scaling constant. So just like if you knew, for example, with the exponential tilting, if you had this case, say you had a really weird distribution, Weibull distribution, and then you do this exponential tilting on it, and you want to simulate from the exponentially tilted Weibull, you can't actually calculate what this m theta at the bottom is for that. For Weibulls, you just don't know that number. So you only have access to the density that you want to simulate from up to a scaling constant. So you don't even have access to the density. And so with this Markov chain technology, that doesn't matter. Even if you know only up to a scaling, that's good enough. But maybe this will, if I keep going, it'll make more sense. So the problem I was just describing before was that if pi is the thing you want to simulate from, and you could simulate it from it once, and you had this Markov chain, you could keep simulating it from it more and more times. But the problem is, how do you get the first one? So that's where another aspect of Markov chains comes in handy, which is the limiting distribution. And that is basically the case that if you start a Markov chain anywhere, at any point, and you just look forward in time equals 1, 2, 3, and you just keep going forward, you eventually actually get to, if you look at, say, what is the distribution of the Markov chain at time 1,000,000 or time 1,000,000,000? If you keep going into time infinity, it has some distribution, which is pi. That is to say that the limiting distribution is the same as the stationary distribution. So if you wanted to simulate from pi in this case, you could just start a Markov chain anywhere and just let it run for a very long time. And then, let's say, for example, here what I've written is to simulate from pi, you start xdot anywhere and run it for n equals infinity time. So that's a perfect world. If you run it at n equals infinity, then at that point it'll be distributed as pi, and then infinity plus 1 is also distributed as pi, and infinity plus 2 is also distributed as pi. So obviously we don't have the patience to let anything run for infinity amount of time. So what MCMC does is you let the Markov chain run for a while, a long time, and we'll say this is perhaps the best approximation in all of applied mathematics. So just let n be approximately infinity for some n. So then at that point you have xn is approximately simulated from the thing we want, pi, and xn plus 1 is approximately simulated from pi. So I should point out that if, as I was saying in last week's lectures, all of the methods I'm giving you are worse than the previous ones. Like this method is worse than crude Monte Carlo, because with crude Monte Carlo, you get, assuming you can do it, you get samples which are independent. That means they have more information. Each sample has more information in it than if they're dependent. They're sort of repeating the same information in a sense. And you're simulating from them exactly. Here, with the MCMC, you're simulating from them approximately, and they're dependent. But yeah, as I was saying, when things are really difficult, you just have to do this kind of disgusting tricks. So I wanted to come up with an example of a Markov chain to make some plots. And so the following is what I came up with. So you define a Markov chain by how you move. I'm at this one position, how do I move to the next position? And imagine a stochastic process that if I know I am at little xi minus 1, to get to the next xi, I do a jump of size capital EI, which is exponentially distributed. So I sample an exponential distribution, and I either jump left, and that's to say my next position is where I was, subtract the E, or I jump right, which is where I was plus the E. And the rules for jumping left and right are like this. If I was previously below minus 1, I jump right. If I was previously above 1, I jump left. So if you think about it on the axis, outside of minus 1 and 1, you're always sort of jumping towards 0. And then if you're in that area between minus 1 and 1, you jump in each direction with some different probability, which is this thing here. So let's see if we can make this work in R. So we'll set lambda just to be some value 5. And we'll look at how do you generate a transition. Given that I'm at x, how do I generate the next position? So the rule says that I'm jumping by some size which is exponentially distributed. So in R, that's R_exp. And I want one jump. And lambda is the rate that I've decided. That's just going to say how big the jump size is. So I can put these rules in straight away. So if where I am is less than minus 1, I know that I'm just going to return the next position is going to be R plus E, because I'm jumping right. If I'm above 1, I'm going left. Otherwise, there's some probability of jumping either left or right. So probability of jumping left, 1 plus x plus 1 squared divided by the same thing except with the plus and a minus. Does that work in R to have it written like this? We'll soon find out. So then to say that something happens with a probability, like with a specific probability, you just sample a uniform random variable and say, is that less than or equal to my threshold? So runif one, if that uniform is less than my jump left probability, and then again I go x minus the jump e. Otherwise, we're jumping right. So let's see, for example, what happens if I'm at 0. Okay, so oh yes, you're totally right. So around 0, I'm getting some positive values, some negative values. That seems fine. What about it, like some huge number, 100? I'm always getting numbers that are just under 100, so I'm jumping left. That seems to be working. And then a large negative number, I'm getting numbers which are greater than minus 100, so the code seems to be working. Okay, so let's see if we can plot these things to see what they look like. So what's the PDF of going to y given that I started at x? Okay. Sorry. Okay. So if I jump left, then that's the density of an exponential evaluated sort of centered on x and in the y direction. No. And if I jump right, it's the density of a random of an exponential the other way, to the right. And the same thing as before, if I'm below -1, then I'm jumping right, so I can return that thing. If I'm above 1, I'm jumping left. Otherwise, I'm doing some random thing. I'm jumping left with probability. Let me just copy that from the previous page. With that probability, I'm jumping left. So the density of the resulting thing is a mixture distribution. So the mixture of two exponentials, you return the probability of hitting one of the mixtures, so prob jump left, multiplied by the density of that mixture component, and then plus the other mixture component, which is probability of jumping right, otherwise known as 1 minus the probability of jumping left, times that. So let's see if that works by plotting it. Now this is particularly where I dislike R, because the plotting is so disgusting. I literally took like my laptop to my friend Pierre Livier's office, because he's the one that teaches the introduction to R class now, to get him to do the R plots for me. And I've concluded that I'm just not going to plot in R ever in my life. I don't have to. So we'll get some grid of x values to look at on the x-axis, and we'll say if I'm at position 0, look at the probability of where I'm going next from that. Or if I'm at position minus 0.5, then also tack that onto a list. Or look at if I'm at position plus 5, and then just for good measure, some ones that are outside of the range, minus 1 and 1. Okay, so the only way I could find R to make some plots all at the same time is to put them into a matrix, and then to use matplot. Okay. Try to make it so that you can see it. No, that's barely visible. So if we're with this Markov chain, this bizarre example that I came up with, what we're looking at is where am I going next, these transition probabilities. So if I'm at 0, that's this black line here, the distribution of where I'll end up next is this. It's actually a Laplace distribution. If you move with an exponential distribution in one direction or the other direction, that's actually a Laplace distribution. Anyway, or so basically you go either left or right equally with equal probability. If you're out here on the edges, the blue, it's pretty hard to see that one either, then you're only moving towards the middle. It's just 100% moving that direction. And in between, like this red one here and that light green one, if you're between, say, 0 and 1, this is heavily pushing you to go towards 1. Or if you're between minus, I'm doing this backwards for you, minus 1 and 0, then you're heavily going towards minus 1. So that's what this thing is that I defined. So I've thought it might be instructive to show you how to vectorize this thing. And so, well, I guess I should explain first are you guys familiar with that term, vectorizing a function? Or? No. Okay, so I guess for the people that don't like programming or haven't done much of it, there's a common thing with R and Python and most languages is when you're doing mathematics, the language prefers to work with vectors, prefers to work with matrices. And things are much more efficient when you write in terms of them. So we can try to redo this function in a vectorized way. And by that I mean, if I'm given a position of x, a vector of x locations, and I want to say I'm given a position of 100 different Markov chains that are running at the same time at position time equals 10, and I want to push those 100 Markov chains forward to time 11 all in one go, we would use this kind of function. So to do that, you start off by figuring out how many Markov chains are running at the same time. That's the length of the vector there. And then for each Markov chain, you would need to simulate a jump size. So your Rx boosts up. Instead of simulating one jump, you need to simulate a different jump for every chain. And then, actually this code doesn't need to change at all. Before it was just one number, a probability of just 0.7 or 0.2 or whatever. And because if you put in a vector instead there, it'll just calculate that probability for each x and give you that probability of jumping left for each of the Markov chains. So just let it do its magic, don't need to change anything there. And then we'll make a vector which is true or false for each Markov chain, and we'll say, is it jumping left? And one way to do that is to flip the coin. So if we flip a coin for each of the R Markov chains, so R unif R will give you capital R number of coins to be flipping, and then prob jump left, that'll weight each of the coins differently depending on which Markov chain you're looking at. And so you'll get this jump left will be some random vector of true and false for each of those Markov chains. Is it jumping left? The only thing wrong with this is that this is not actually accurate. If you're inside -1 and 1, this is perfectly fine. But if you're outside that range, it's not random which way you're jumping. You're definitely jumping in one direction or the other. So if for those specific values that are outside the range, you say which x's are less than -1, well then they're all definitely jumping right. Or all the ones that are greater than 1, they're all definitely jumping left. Okay, so now we can just say that where they are at the next time position is where they used to be, plus the jump. If we just did plus the jump size, then they're all jumping right. So we need to make a way to flip, to add in the sign plus or -1, depending if our vector here jump left has a true in it or not. And the way to do that is you can take the -1 and put it to the power of jump left. And so this is just something in most programming languages, that true and false, if you start doing math with true and false, like if you go, what is 2 plus true, it normally converts true to the number 1 and false to the number 0. So 2 plus true is usually 3 for most languages. And in this case, it happens to work the same. If you go, what is -1 to the value to the power of true, that's really -1 to the power of 1, which is -1. And -1 to the power of false is -1 to the power of 0, which is plus 1. So,
what is ES?
Good question. It's not there. There is no ES. I'll delete that from the lectures recordings too. There's no mistakes. So let's test that out. So if we put in a vector of locations, -1.5, 0, 1.5, and voila.